A logarithm is the inverse of an exponent. A logarithm is the operation you would use to figure out what the exponent is in this equation. 2 to the power of x equals 8. Then x will be the log base 2 of 8. Or as another example, if you have, say, 3 to the power of x equals 9, then to solve for x is the log base 3 of 9. So in the first case here, the log base 2 of 8 asks, what exponent do you need on 2 to get 8? Well, a little bit of mental arithmetic, and you can work out the answer is 3. In this case here, the log base 3 of 9 is asking what exponent on 3 gives you 9. Again, a little bit of mental arithmetic, and you would figure out the answer is 2. More generally, we can write that if you have b to the power of x equals n, then x is equal to the log base b of n. The way I've written this here is the opposite of what you would see in most textbooks, and that most teachers would explain. The typical textbook or teacher would show you b to the power of x equals n, then the log base b of n is equal to x, which is clearly mathematically equivalent to what I wrote. However, it hides the algebra. In this version here, you can see very clearly that the b is going to the other side as the base of a logarithm. In this version here, that's less clear. This method here is similar to saying if you have x plus 2 equals 5, then x is equal to 5 minus 2. The 2 goes to the other side with the opposite operation. The b goes to the other side with the opposite operation. Here, this version, if x plus 2 equals 5, then 5 minus 2 is equal to x, which is absolutely true, and is a way that subtraction might be shown to start with in, say, grade 2 or 3 before a student has learned about algebra. But once you have a familiarity with algebra, this version here should be more intuitive to explain an opposite operation and to explain how logarithms will get used in practice. Note that exponents have 2 opposite operations. If we have, say, 2 to the power of 3 equals 8, we could rearrange this equation in 2 different ways. 2 would be the cube root of 8, and 3 would be the log base 2 of 8. Exponents are unique in what I would consider the basic operations, adding, multiplying, and exponents, in that it has 2 opposite operations. Adding 2 plus 3 equals 5 only needs 1 opposite operation. 3 is equal to 5 minus 2, and 2 is equal to 5 minus 3. That's because addition is commutative, or the order of adding does not matter. Therefore, the positions are effectively the same. The same is true with multiplication. 2 times 3 is 6, so 3 is 6 divided by 2, and 2 is 6 divided by 3. Multiplication is commutative, the positions are effectively the same, therefore the same opposite operation is used for either position. Exponents are not commutative. 2 to the power of 3 is different from 3 to the power of 2. Therefore, we need different opposite operations depending on which part you're trying to find. Let's do a few basic examples. How about if we have, say, 2 to the power of x equals, let's go with 16. Then to rearrange this, you would say x is equal to the log base 2 of 16. And we would want to know 2 with what exponent gives you 16. This logarithm is effectively asking 2 with what exponent gives you 16. Well, which is effectively the same as the original question. A little bit of mental work, you can figure out that 4 2's multiplied together gives you 16. Let's consider, let's say 2 to the power of x is equal to 1 over 4. That should be interesting. This means that x will be the log base 2 of 1/4. Or 2 with what exponent gives you 1/4? That's a little bit tricky. We could do a few steps here. You might be able to work it out at one step in your head, but we could rewrite this as 4 to the power of -1. 4 to the power of -1, if you remember your exponent rules, is the same as 1/4. 4 itself is the same as 2 squared. So this would be the log base 2 of 2 squared to the power of -1. Again, another exponent rule, these exponents will multiply. So this is the log base 2 of 2 to the -2. This question, kind of like that one, is effectively asking 2 with what exponent gives you 2 to the -2. Well, there it is. It is simply -2. And looking at that, you can see that a log base 2 and a 2 to the exponent cancel each other out. You get just the exponent, which makes sense because a logarithm is meant to be the opposite of an exponent operation. So the logarithm and the exponent canceling out seems like an obvious thing, meaning that the log base b of b to the power of x will always be x, as a general rule. Here's an example where we might use logarithms to work out something that might actually seem useful. This is the equation for compounding interest. Suppose we start with an amount of money, say $1,000, at an interest rate of, let's go with 4%, which we'll have to convert to the decimal form, 0.04. And let's say we want to know when that amount of money will double to $2,000. In this case, n will be the number of years it takes this amount of money to grow to this amount of money at this interest rate. So the amount of years that it takes $1,000 to grow to $2,000 at a 4% per year interest rate. We can plug in the numbers. 2,000 is equal to 1,000 times 1 plus 0.04 to the power of n. At this point, it's a little bit of algebra to work things out. 2,000 is equal to 1,000 times 1.04 to the power of n. We want to isolate n. The next thing we need to deal with is that 1,000. So we can divide both sides by 1,000. 2,000 divided by 1,000 is 2, and those 1,000s cancel, and we have 1.04 to the power of n. This is where logarithms are going to come in. We want to solve for the exponent, so the base of the exponent can come to the other side as the base of a logarithm. This is the logarithm we need to solve. Pulling out our calculator. The log base 1.04 of 2 is 17.7. So n is 17.7 years. So that means it will take almost 18 years for money to double at a 4% interest rate. You could repeat the calculation with other interest rates if you like. You can put in, of course, any numbers you like. The logarithm allows you to solve for the exponent.